Okay, I think we can get started. Today we will introduce a review paper. It talks about the self-supervised representation learning. Here's an overview of this paper. I think the biggest contribution of this paper is a very systematic review of self-supervised learning approach. The intuition behind this self-supervised learning approach is that it uses a pre-text task for learning good feature extractor, and this good feature extractor will be used in the downstream task. And this paper is published in 2022 in the Signal Processing magazine from IEEE. Okay, first we will do some comparisons between this self-supervised learning and the supervised learning, and also this unsupervised learning. So these three different learning approaches. So for supervised learning, usually we have a set of label data. For example, this is the input, this is the label output. We use this input and label pair to calculate the loss. And during this process, we have a feature extractor H theta that the extractor used for meaningful representation from this input. And then we have a task head. This task head can be, for example, for classification, object detection, and image segmentation. Yeah. And it gives us the prediction, and we combine this prediction and the ground truth to calculate loss. So in supervised learning, the key thing is we require the dataset to be a labeled dataset. Examples of this approach includes this VGG and the ResNet, also this InceptionNet for lateral image classification, for example. For unsupervised learning, usually we have unlabeled data. We only have, for example, we only have the input image in the computer vision domain, and we learn the feature extractor also, and then we learn another task head. In this particular situation, this is a reconstruction task head. So we reconstruct the whole image, and then we combine the reconstructed image with the original input image to calculate the loss. And this loss will be used to train the task head and also the feature extractor, theta and the phi. So as you can see, the important thing here is we need to reconstruct the input to calculate the loss. Examples using unsupervised learning include this VAE variation autoencoders and all this generative Wadsworth nets. Some classic generative unsupervised learning approach include these Gaussian mixture models. For self-supervised learning, it's a little bit different. So we still have only an unlabeled data set. We only have the input, for example, but from this input, we can generate a label. Basically, we construct a labeled data set, and then we use this constructed labeled data set to train a feature extractor and also a task head for this particular task. And the end goal of this approach is just a feature extractor. This feature extractor, once it's trained, will be used in the downstream tasks. Yeah, just as we mentioned, so for this task, we have a label. This label is generated, manually generated, and we have a feature extractor and also a task head for this particular task. This task generates this labeled data set, and then we train. After we train this model, we get the good feature extractor. So examples of this approach include this MOCO and the SimCLR. Okay, now let's talk about how this supervised learning can be used in practice. So usually we have in the very beginning, we start from an unlabeled data set. For example, here we have a cat image for this stock and this stock image. For this stock image, for example, we will apply some transformation, and this transformation will give us a label and some input. So this input and label pair will be used in the pre-text task training. For example, here, this input, if for example here, suppose the input here is the same as the original image. So this image will go through a feature extractor, and we get a feature representation, and this feature representation will be fed to the task head in the pre-text task. So it just give us the output, the label prediction in this pre-text task, and this pre-text task will be combined with the ground truth label in this pre-text task. Then we get the loss, which then train this model. So once this model is trained, we take out the feature extractor, and we use it in a downstream, for example, task or labeled using a labeled data set. For example, here we have a data set with both the input and label pairs, and this input and this labeled data set will be used to fine-tune this feature extractor a little bit, and also a new task head specified for this particular task. The intuition behind the main, basically the motivation for this self-supervised learning is that this self-supervised learning training can help us find a feature extractor pretty close to the local optimal feature extractor for this target task. So in this situation, since it's very close, so we can simply fine-tune it a little bit to get a really good feature extractor for the target task here. So what are the possible pretext tasks? So here are some examples. It talks about how can we generate different input and the label pairs in this pretext task. For example, the first one is we use this transformation prediction pretext task. So for given image from the unlabeled set, we will do some rotation for this image, and for this rotation parameter, we know it. We can use it as a ground truth, and we then use the transformed image as the input and the pretext task. Then in this case, we have a paired label and input and label input. And another task is we just mask part of the image, and then we use the mask part as the ground truth, and use the rest of this image as the input. Then we want to predict from its input the masked content. So in this approach is called this masked prediction pretext task. So another approach is instance discrimination. So in this approach, we treat each of the unlabeled image as a unique class. For example, this cat, it will those three images are about cat, but we will give them different labels and treat each of them as one particular class. So in this case, we can do just the cross entropy loss, since the pretext task is just a classification task. But the problem is we can probably have a very large number of classes. Another approach is this clustering approach. The key steps include we first applying a clustering algorithm to the enabled data set to learn these different clusters. And then we will assign those different clusters different labels. And then we will use these procedural labels under the input data, image data to train a feature extractor. Because at this step we can think of we have already had a labeled data set. We just train the model as a regular classification training task. And another way for designing this pretext task is this contrastive instance discrimination. The key idea is, for example, for given image, we will obtain a sequence of images, and for this sequence of images, some of them are in the same class as this image, but some of them they are not. So this there will be some discrimination between this sequence of images. We will make use of this to design the pretext task. For example, the task can be we need to determine whether this image is in the same is it about the same object or not. For example, here these two images they are about the same object, so we give it a pair label 1. And for these two images, since they are of different objects, then we give it a label pair label 0. Okay, more specifically for the mask prediction task, the algorithm is like this. We have an enabled dataset. It contains a sequence of images, and for each of this image, we will just generate a mask indices, a set of indices, and these indices will correspond to the content that will be masked, and this mask content will be used as the label in the pretext training task. Similar for this transformation prediction, we apply a transformation and we get a new input. This new input will be used in the pretext training task, and this parameter will be used as the ground truth label in this pretext training task. And for the contrastive instance discrimination, as we just mentioned, for example, for each of these images, we will sample one from the transform. We apply basically in the first step is we get a distribution of the image. This distribution you can achieve this by for example these different rotations, for example 5 degrees, 10 degrees, and 25 degrees. Then you have a sequence of images. These images are just of different rotation degree, and you sample one of them as the anchor label, and then you sample another one from this distribution. Then for these two images, so they are from the same distribution, they should have this pair label 1. And we also sample K images from some other distributions, and for this other distribution, since they are not from the same distribution as this anchor image, so for all these other pairs, we will give them the label, basically the pair label 0. So the final input and the label data pair for this pretext task is actually a sequence of image pairs, and also a sequence of label, the pair labels. Okay, so about the clustering pretext task, it's also pretty simple. For example, we have a enabled dataset, and we will get a feature representation for all these images, and then we do a clustering to get the centers of all these images, of course, in the feature representation space. And with all these cluster centers, we will assign each unlabeled image a label, and this label is basically the cluster index that is closest to the input to the image. Then finally, we will get a labeled data set. So this labeled set will be used in the pretext training task to train the feature extractor and also the pretext task head. Okay, here are some concrete examples of this transformation pretext task and also this masking prediction pretext task in different modalities. For example, in video modality, the transformation can be reordering of the images. And in text, yeah, same thing, we can do the reordering of this different text sequence. Similarly for this audio and this graph. And for the masking task in video, we can just mask off some frames, and in text we can just mask out a chunk of text, and in audio we just mask out a segment of the audio. Similarly, in the graph, we just mask out some of the nodes and use this node as the ground truth label in the pretext task. And then we train the model. Okay, here is a table summarize these self-supervised learning approaches in different modalities, and also it also tells us whether the code and the pre-trained models are available or not. And for these different image modalities, the commonly used data set are also introduced. For example, in imaging, in computer vision domain, so ImageNet and this YFC 100 million and this iNaturalist images. So they are the commonly used data set for self-supervised learning tasks. So what about the performance of this self-supervised learning approach? Can it really give us any benefit? And the answer is yes, it can even surpass the performance of fully supervised learning approach. For example, here, if we check the supervised learning approach performance at the baseline with 1, then some of this self-supervised learning approach can go far beyond the performance of this supervised learning approach. And similar in the tasks, in the natural language processing tasks, this self-supervised learning approach can surpass its human scores. For example, this earlier 3.0, it achieves a super glue like overall score above human score here. Okay, that's all. Thank you.